welcome to the next session of Subject Engineering Mathematics, Chapter 2, that is Differential Equations. Now, let us see what we discuss in differential equations. In differential equations, generally, we have two types of differential equations. One is ordinary differential equations and second one is partial differential equations. Ordinary differential equations and partial differential equations. Now let us see the basic difference between these two. Let us start with few basic examples. Suppose if I have equations like this, dy by dx equal to 2x plus 3. Now this is an ordinary differential equation. When you look at partial differential equation, terminology will be slightly different. Suppose the equation is like this: dou square u by dou x square equal to dou square u by dou y square. Now this is an ordinary differential equation, whereas the second equation is a partial differential equation. Let us see the basic difference. Here we have two variables, x is one variable, y is one variable. Now in dy by dx, this y is called dependent variable. This y is called a dependent variable and this x is called an independent variable. So therefore, in case of the first differential equation, we have exactly one dependent variable and one independent variable. But whereas in this case, u is a dependent variable. U is dependent variable. But the independent variables are x and y. X comma y are independent variables. Now let us discuss why they will be called as independent variables and why the numerator variable is called dependent variable. Let us start with this. This is dy by dx. Basically this dy represents difference in y and dx. Y is one physical quantity, x is one physical quantity. Dy by dx means change in y divided by change in x. This is change in y divided by change in x. So rate of change of y with respect to x, that is called a derivative. That is called a derivative. Say for example, we always discuss particularly mechanical branch students and civil students, they used to discuss acceleration. So what is acceleration? Rate of change of velocity with respect to time. So we can do like this, dv by dt. So here this v is velocity and this t stands for time. So change in velocity with respect to time, that is called an acceleration. Since velocity is depending on time, this is called dependent variable and this is called an independent variable. Since velocity is depending on time, velocity is called dependent variable and this is called independent variable. That means velocity is a function of t. Velocity is a function of t. Therefore, whenever a quantity is expressed in terms of another quantity, this is called dependent variable, this is called independent variable. We all have some habituation towards the notation y equal to f of x. So that means y is expressed in terms of x, therefore y is a dependent variable and x is an independent variable. Now in case of ordinary differential equation, there will be exactly one dependent variable and one independent variable. But in case of partial differential equation, the notation is slightly different. There will be exactly one dependent variable but number of independent variables is more than one. Say for example, if velocity depends on two physical quantities, say for example time as well as temperature. So this T stands for example, capital T stands for temperature and this small t is time. So if velocity depends on both time and temperature, then I cannot discuss change in velocity of an object with respect to time, with respect to temperature. So I cannot get accurate values. What is the accurate change in the velocity of an object by changing frequently time and by changing frequently temperature? So therefore, when you are measuring partial differential equations, in that case what we do is partial derivatives are possible. So that means when you are finding this dou u by dou x, this y is constant. So in that example, you can easily find dou v by dou t. So change in velocity with respect to temperature. That means the temperature is a variable. In that context, this time is constant factor. So keep the time as constant and find the change in velocity of an object by changing frequently temperature. So when you are finding dou v by dou t, remaining parameters are constants. So that is the basic difference between ordinary equations and partial differential equations. So when you are measuring, this is second order derivative. When you are finding this dou u by dou x or dou square u by dou x square, x is variable, y is constant. When you are finding this dou square u by dou x square, y is a variable parameter and x is constant. So from all these examples, it is clear that the basic difference between ordinary and partial differential equations is, in case of ordinary differential equations, there will be exactly one independent variable, but whereas in case of partial differential equations, they will be more than one. That's why we discuss ordinary derivatives and partial derivatives. Hope this concept is very clear. Now, throughout the differential equations, we have a single goal, that is solving the differential equations. Solving differential equations. What does it mean? So solving this equation is nothing but finding the value of y in terms of x. Solving a differential equation is nothing but finding the value of dependent variable in terms of independent variable. So in this case, I need to get the value of y in terms of x. And in this case, I need to get the value of u in terms of x and y. Therefore, in differential equations, solving a differential equation is nothing but finding the value of dependent variable in terms of independent variables. So these things we do normally in differential equations. And few instructions about solving these points are: one should be very cautious about formulae, basic formulae of differentiation and integration. Once all formulae are very clear, derivatives and integrations are so powerful factors, because in this we were discussing chapter 2 differential equations. Maybe once chapter 2 is finished, we go for chapter 3, that is calculus part. A calculus is completely based on derivatives and integrations. In calculus, we have three types of calculus: differential calculus, integral calculus, vector calculus. For all these modules, the basics are formulae of derivatives and integration. Next, we discuss numerical methods. Again, it is purely based on derivatives and integration. For example, when you go to numerical differentiation, differentiation is important. When you go for numerical integration like trapezoidal rule, Simpson's rule, one-third rule, then we need to go for integrals. And then when you go to a new chapter, complex variables, completely it depends on integration. Complex integrals, that is called contour integration. And if you go to, for example, Laplace transforms, completely it is based on derivatives and integration, transform theory techniques. If you go to probability and statistics, there will be distribution curves. They will be based on completely integrals. So hope you understand. For all rest of the chapters, the basics are derivatives and integrations. Now let me list out the basic formulae of differentiation and integration. So at first, we read differentiation formulae. So we start with d by dx of x power n. So here x is variable, n is constant. This is n times x into x power n minus 1 for any constant. So derivative of x power n is n into x power n minus 1 for any constant n. You can write any value of n, integer value, fractional value, any number. It must be some real number. Next to d by dx of e power x. So this is e power x. Here e is nothing but some constant, that is 2.71, and this is nothing but Euler's constant. Euler is a mathematician who invented this constant. That's why it is named as Euler's constant. Now let us write the extension formula for this. This is a particular constant. This is constant. This is variable. This is variable. This is constant. Now let us write the formula for d by dx of a power x. This is general particular constant and this is general constant. So this is a power x into log a. Now this is nothing but extension of this. When you replace a by e, you get e power x into log e. When I don't specify base value, by default it is e. If a log for a logarithm base is not specified, by default it is e. So we need not mention that this is log a to the base e. If I write log a, by default it is base e. Or we have another notation. This log a can also be written as ln a. ln, natural logarithm. This is nothing but natural logarithm. Natural logarithms are nothing but logs with base values e. Log with base value e. So log a to the base, log a is same as ln a. This is nothing but log a to the base e. Natural logarithm. So replace a by e. We get e power x into log e. Log e to the base e. Log e to the base e is 1. Therefore, from this we get this formula. Formula number 4. D by dx of constant. So there is no, this is a constant quantity. So therefore, with respect to any variable, derivative constant is 0. So d by dx of k is 0 for any constant k. Next, formula number 5. D by dx of sin x. Derivative of sin x is cos x. D by dx of cos x. This is minus sin x. Now I write one general formula. Instead of going for tan x, I write some general formula. D by dx of k1 into f of x plus or minus k2 into g of x. So this is constant, this is constant. Constant is multiplied with function of x. Second constant is multiplied with function of x. So when constants are multiplied with functions of x, they can be taken before derivatives. Therefore, this is k1 into d by dx of f of x. If it is plus, write plus. If it is minus, we get minus. So plus or minus k2 into d by dx of g of x. That means constants can be taken before derivatives if they are multiplied with functions of x. And this is true for any constants k1 comma k2. For any constants k1 comma k2. And this property is called linear property for derivatives. This is called linear property for derivatives. Note all these formulae. Now we write formula number 8. This is d by dx of. In formula number 7, we have covered plus and minus symbols. Now let us take product. So d by dx of f of x dot g of x. Derivative of product of two functions. F of x is multiplied with g of x. This is nothing but f of x into g dash x plus g of x dot f dash x, where this is nothing but derivative of g and this is nothing but derivative of f. So this is first order derivative and this is first order derivative. This is nothing but d by dx of g of x and this is d by dx of f of x. It is a first order derivative. So this rule is called product rule because we got the derivative of product of two functions. That's why it is named as a product rule. d by dx of two functions, product of two functions, derivative of product of two functions. That's why it is called product rule. Formula number 9. Now let us replace this dot by division, f of x by g of x. So in the denominator we have g of x. Priority is given to g of x at first. This is g of x into f dash x minus reverse combination. This is f of x dot g dash of x divided by g of x whole square. And this is called coefficient rule because we got the derivative of coefficient of two functions. So this is product rule and this is coefficient rule. Now based on this, we can easily get the derivatives of rest of the trigonometric functions. Already we have written derivatives of sin x and cos x. Now based on this coefficient rule, we can easily get the formula for derivatives of rest of the trigonometric functions. Tan x, cos x, cot x, secant x, cosecant x, etc. So formula number 10, this is d by dx of tan x. So tan x derivative is secant square x. Because tan can be written as sin x by cos x. And then apply formula number 9, coefficient rule, you get secant square x. D by dx of secant x. This is secant x times tan x. Next, d by dx of cot x. This is minus cosecant square x. Here also the same case. D by dx of cos by sin. Because cot x is cos by sin. Now we can apply formula number 9. Derivative of secant x. Secant you can write it as 1 by cos. Then apply coefficient rule. Formula number 13. D by dx of cosecant x. This is nothing but minus cosecant x into cot x. Minus cosecant x into cot x. So therefore, by using this formula number 9 and d by dx of sin x is cos x and using derivative of cos, easily you can get the formula for this. Tan is sin by cos, apply coefficient rule. 1 by cos, secant, apply coefficient rule. Cot x, cos x by sin x, apply coefficient rule. This cosecant x is 1 by sin x, apply coefficient rule. Easily you will get these values. Note this formula. Now let us write the derivatives of inverse trigonometric functions. D by dx of sin inverse x. This is 1 by square root of 1 minus x square. Next, d by dx of cos inverse x. So this is minus of this. Minus 1 by square root of 1 minus x square. So this is plus 1 by root over 1 minus x square. This is minus 1 by root over 1 minus x square. Next to d by dx of tan inverse x. This is 1 divided by 1 plus x square. This result is very useful while solving many GATE and IES questions. Derivative of tan inverse x is 1 by 1 plus x square. Next, formula number 17. D by dx of cot inverse x. This is nothing but minus of this. Minus 1 by 1 plus x square. Next, formula number 18. D by dx of secant inverse x. This is 1 by x into square root of x square minus 1. Next, d by dx of cosecant inverse x. This is nothing but minus of this. Minus 1 by x into square root of x square minus 1. Now, when you look at all these formulae, formula number 14 and 15, they belong to one category. This is plus 1, this is minus 1, except that everything is same. Here also this is plus 1 by 1 plus x square. This is minus 1 by 1 plus x square. And this is 1 by x times square root of x square minus 1. This is minus 1. So try to remember this particular sequence. These two belong to one category. These two one category and these two one category. And we need to write one more formula, that is d by dx of log x. Here base value is e, 1 by x. Now when base is different number, suppose I want d by dx of log x to the base 4. How to get this? Here d by dx of log x is 1 by x. What is base value? It is e. Now if I have different base, then how to get this? So first of all, note down these points. We will come back to d by dx of log functions with base other than e. Now let us come back to find the derivative of log x to the base value other than e. So my task is to find d by dx of log x to the base 4. So this is formula number 21. I want d by dx of log x to the base 4. Now to get the derivative of this, try to convert this logarithm into log with base e. We have a result in the logarithms. Log a to the base b is equal to log a divided by log b. This is general base. Log a to the base b is log a divided by log b. Now in the left side part, the base is b. On the right side part, the base values are e. Therefore, this can be written as d by dx of log x divided by log 4. Log 4. Now therefore here base is e, base is e. 1 by log 4 to the base e, it is a constant quantity. But constant is multiplied with log x. So this can be taken before derivative. Constant is multiplied with function of x. It can be taken before derivative. Therefore, this is 1 by log 4 into d by dx of log x. So derivative of now base is e. Therefore, this is 1 by x times log 4 to the base e. So this is the way to find the derivative of log function with base value other than e. Next, I want d by dx of x power x. Now both are variable quantities. Earlier we have seen d by dx of x power n. Now this is variable, this is constant. Next we have written the formula for derivative of a power x. This is constant, this is variable. After that we wrote the formula for derivative of k. This constant we can write it as k power k. So variable, constant, constant, variable, both are constants. Now the next point is d by dx of x power x. So four choices will come. Variable, constant, constant, variable, both are variables. It refers to single constant. Constant power constant is constant, its derivative is 0. Now we refer to two variable points. So base value is variable and even power is variable. Now let us try to get this one. So to get this, take y equal to x power x. Now apply log on both sides. Log y equal to log of x power x. This implies log y equal to, now here power is x, it comes before log. So x times log x. So we call it as equation 1. What is our task? We need to find d by dx of x power x, but y is x power x. So I need to find dy by dx. So differentiate equation 1 with respect to x. We get 1 by y times dy by dx equal to, now apply product rule. This is f of x, this is g of x. Apply product rule. X into derivative of log x is 1 by x plus log x into d by dx of x1. This x will get cancelled. This implies dy by dx equal to y into 1 plus log x. This implies d by dx of This y is nothing but x power x equal to x power x into 1 plus log x. So the formula for d by dx of x power x is x power x into 1 plus log x. So simply we have applied log on both sides and then we have applied product rule to get its derivative. Note these two formulae. So next we write integration formulae. Now before discussing integration formulae, one simple point is, once all differentiation formulae are very clear to you, now integration is a simple task, very simple task. Let me tell you one example. Suppose if d by dx of f of x equal to g of x. If d by dx of f of x equal to g of x, derivative of this function is g of x, implies integral g of x dx equal to f of x. Implies integral g of x dx is f of x. Derivative of f is g, implies integral g of x dx is f of x. Of course, we can write constancy, but generally we will write the constancy during solving previous gate questions or IES questions, etc. But generally, meanwhile, throughout this session, when we write the integration formulae, it is not required generally to write C. But let me tell you the importance of writing constancy in the integration formulae. So what is this C? General constant. Let me tell you one simple example. Suppose d by dx of x square. This is derivative of x power n. This is 2x. That means, according to this rule, integral 2x dx equal to x square. So derivative of x square is 2x. But don't think that this is the only function for which the derivative is 2x. I can write 1 also. Because the derivative of x square plus 1 is 2x. In place of 1, we can write 1 by 2 also. Derivative of x square plus 1 by 2 equal to 2x. Or we can write d by dx of this integral 2x dx is x square plus 4. Because the d by dx of x square plus 4 is 2x. So instead of writing different particular constants, say for example 2, 4, 1 by 2, etc., generally we write the constancy. This is the basic reason behind this, why we are adding constancy when you are doing integration, right? I think this point is very clear. So whenever d by dx of f of x is g of x, implies integral g of x dx is f of x plus c. This c is a general constant. But in this session, when we write formulae, let us do not maintain that formality of writing c. We can write it direct formulae without writing c. But during solving gate questions or IES questions, we need to write definitely. That depends on order of an equation, right? So formula number 1, integral x power n dx. Integral x power n dx, n is some constant. This is x power n plus 1 by n plus 1 if n not equal to minus 1. N is any constant except minus 1, because in the denominator we have n plus 1. So when you take n value minus 1, denominator gets 0. Something divided by 0. So something divided by 0 is undefined quantity. Therefore, in the mathematics world, denominator should not be 0. Therefore, make sure that this n value not equal to minus 1. Now, interestingly, when you observe this integral, when you integrate x power n, power is rising. When you are differentiating x power n, the formula is n times x power n minus 1. So, power is reducing. When you are integrating x power n, the power is increasing. So, differentiation means power will be reduced for powers of x. When you integrate powers of x, powers will rise by 1. So, try to understand these points. So, in this case, integral x power n dx is x power n plus 1 by n plus 1 if n not equal to minus 1. That is, it is true for all constants except minus 1. Now, if n is minus 1, so integral x power minus 1 dx. X power minus 1 means 1 by x. So for which function derivative is 1 by x? Log x. Therefore, integral 1 by x dx is log x. Integral 1 by x dx is log x because d by dx of log x is 1 by x. Next, integral e power x dx. This is e power x only because derivative of this is this. Next, integral a power x dx. This is general constant, this is particular constant. This is given by a power x divided by log a. When you are differentiating a power x, we are getting a power x into log a. When you are integrating a power x, we are dividing with log a. We are dividing with log a. Let me give some clarification why we are doing for differentiation and integration in the different manner. Let me explain after some time. So, integral a power x dx is a power x by log a. Formula number 5. We write integral k1 into f of x plus or minus k2 into g of x dx. So, k1 is multiplied with f of x plus or minus k2 is multiplied with g of x. So, this is similar to derivative formula. When we were doing differentiation, constants are taken before derivative. The same case repeats even for integrals also. So, this is k1 times integral f of x dx. If it is plus, we get plus. If it is minus, we get minus. Plus or minus k2 times integral g of x dx for all constants k1 comma k2. For all constants k1 comma k2. This is called linear property for integrals. Just like derivatives. Linear property for integrals. Now, formula number 6. See, when you look at this, rule number 2, we have integral 1 by x dx equal to log x. Integral 1 by x dx equal to log x. Basically, this is a rational expression. Rational expression. Rational expressions are nothing but expressions in the form. Basically, this is a rational expression. Rational expressions are nothing but expressions in the form p of x divided by q of x. Just like rational numbers. So, rational numbers generally they have a structure integer divided by integer. When the numbers are in the form integer by integer, they will be called as rational numbers. It is related to expressions also. When there is some expression divided by some expression, of course, denominator expression is a valid expression, which should not be 0, then it is called rational expression. So, in this case, we are finding integral of a rational expression. So, the derivative of x is 1 with respect to x. So, that means that the derivative of denominator part is available in the numerator. That's why it is a log of denominator. So, when I generalize this, I get integral f dash of x divided by f of x dx equal to log f of x. So, f of x is written in the denominator part. Its derivative is written in the numerator part. So, its integral is log of denominator. This is so powerful while solving many gate questions. Very important formula. Note all this. So, formula number 7, integral sin x dx equal to minus cos x. As we know that cos x derivative is minus sin x. Already minus is here. So, d by dx of minus cos x is plus sin x. Its derivative is minus sin x. Already minus is there. So, derivative of minus cos x is sin x. That's why integral sin x dx is minus cos x. Next, integral cos x dx. This is simply sin x. Next we move to integral tan x dx. This tan x can be written as sin by cos. Now this is integral of a rational expression. Integral of a rational expression. So cos x derivative is minus sin x. There is no minus sign, but constants can be manipulated with integrals. So multiply with minus symbol, one minus symbol outside. Now cos x derivative is minus sin x. Therefore, according to formula number 6, this will be minus log of numerator denominator. This is cos x. So therefore, this is log of, this minus appears as a power of cos x. So log of cos x whole power minus 1. This is log of cos x whole power minus 1. 1 by cos x. So this is secant x. Just by applying rule number 6. Next formula number 10. Integral cot x dx. This cot x can be written as cos by sine. Cos by sine. So sin x derivative is directly cos x. Again, by using formula number 6, this will be log of this denominator. We get log sin x. Next we write integral secant x dx. Now you cannot get directly in this case, because just like formula number 10 and formula number 9, when you write secant x as 1 by cos x. Suppose when you write secant x as 1 by cos x, there is no advantage for us, because cos x derivative is not 1. Cos x derivative is minus sin x. Okay, here I will multiply with minus sin x. Then this denominator gets again minus sin x. Therefore, this expression becomes integral minus sin x by cos x into minus sin x. Now, extra we are getting minus sin x in the denominator. This cannot be taken before integral because this is a variable part. Therefore, when you write secant x as 1 by cos x, you cannot apply formula number 6. Therefore, what I do is, I will multiply this expression with the secant x plus tan x. So, integral secant x into secant x plus tan x whole divided by secant x plus tan x dx. Now in this case, the denominator function is secant x plus tan x. Now basically this is integral, this is secant x into tan x plus secant square x divided by, this is secant x plus tan x dx. Now when you look at the denominator, it is secant x plus tan x. Secant x derivative is secant x into tan x. Tan x derivative is secant square x. This is plus symbol, the same symbol is repeated here. So therefore the denominator derivative is directly in the numerator part. Therefore when you apply formula number 6, this will be log of secant x plus tan x. Log of secant x plus tan x. Note all these formulae. Next we move to integral cosecant x dx. Integral cosecant x dx. The same case repeats even for case 12 also, I mean formula number 12. If you write cosecant x as integral 1 by sin x dx, no benefit for us because sin x derivative is not 1. So therefore to apply rule number 6, what we do is multiply numerator and denominator with cosecant x minus cot x. So this is integral cosecant x into cosecant x minus cot x divided by cosecant x minus cot x dx. Now this is nothing but integral, this is cosecant square x minus cosecant x into cot x. This is cosecant x minus cot x dx. Now let us try to apply formula number 6. Now cosecant x derivative is what? Now here it is minus cot x. So cot x derivative is minus cosecant square x. Already minus is there. So the derivative of minus cot x is plus cosecant square x. Cosecant x derivative is minus cosecant x into cot x. Therefore, the derivative of cosecant x minus cot x is cosecant square x minus cosecant x into cot x. So, its derivative is directly in the numerator part. Therefore, according to formula number 6, this is log of cosecant x minus cot x. Next, formula number 13. Integral 1 by a square plus x square dx. A is some general constant. Suppose if a square is 1, integral 1 by 1 plus x square is a tan inverse x. Now this is general constant. So we get the result in terms of tan function. 1 by a into tan inverse of x by a. This is 1 by a into tan inverse of x by a. Now if I write 1 by x square minus a square dx. Integral 1 by x square minus a square. This is 1 by x square plus a square. This is 1 by x square minus a square. Now this can be written as 1 by x minus a divided by 1 by x plus a into dx. But when you simplify this, the numerator will be 2a. So divide with 2a. Now 1 by 2a into integral this. Simplify this expression, we get 2a divided by x square minus a square. 2a gets cancelled. So 1 by 2a into, apply linear property because between two functions we have a minus symbol. So this is integral 1 by x minus a dx minus integral 1 by x plus a dx. So this is 1 by 2a into integral 1 by x minus a log of x minus a minus log of x plus a. Log a minus log b. So this is 1 by 2a into log of x minus a divided by x plus a. Therefore, in this case, the result is 1 by 2a into log of x minus a by x plus a. Note all this. This is the end of this particular session. We continue some more integration formula in the next session. Thank you so much.